Okay. So now we are on the second module of Internet of Things. So this is networking layer protocols actually. We were talking so far at the data link layer. Now we are at the next layer, which is networking layer. And we will talk about at least two protocols, if not more. And those two protocols would be 6LoWPAN and RPL. But this lecture is just now, and this handout is just 6LoWPAN. Before I talk about 6LoWPAN, I need to talk about 802.15.4. Now, here is the problem that I run into in most of the IoT stuff is that if anything is wireless, you guys have not taken wireless course. 473 goes very little into wireless. So either I teach you wireless a lot, which means then I cannot teach anything else, or I just let you take the next semester. So I am not going to cover 802.15.4, which is covered in the 574 next semester. I'm just going to give you one slide summary of this. Just like I gave you one slide summary of RFID, this is a whole class in 574. 15.4 is probably multiple classes in 574. Here I'm going to give you one slide. Basically 15.4 is used in home environment for connecting sensors together. And sensors means your thermostat with power connectors and things like that. And so the key thing to note about 15.4 is that it is mesh networking. Mesh means that somebody will take your message and transmit. So I send it to you, and we are all routers. Not all. Some people are router. We send it to the router. Some people act as a router, and then they also act as their own end systems. And then so they call full function devices. Full function devices can forward the packet to other nodes. So we don't have to have direct connection, just like in IP. This is data link. Okay? But in the data link, they have mesh networking. Yeah.
So what is the difference between the mesh networking and ad hoc networking?
Okay. What is the difference between mesh networking and ad hoc networking? So the ad hoc is opposite of centralized, if you want to call it that way. All right? When you have a Wi-Fi here, you talk to the base station, to access point, right? This is what we call infrastructure based Wi-Fi. But if you didn't have access point and you had two computers like this and that, and they wanted to talk to each other without the access point, that is ad hoc. Okay? Ad hoc means there is no centralized. So if they had 4 computers, they could still talk to each other without any access point. That is ad hoc. Okay? So ad hoc means no central point of controller. Yeah.
So then would it be fair to say that all the ad hoc networks are mesh networks, but not all mesh networks are necessarily ad hoc networks?
Okay, just the opposite.
No.
Actually, okay, hold on. I didn't say that. Here is an example. 15.4 is a mesh network, but it is not ad hoc. There is a central controller.
Yeah, exactly. So mesh networks.
Okay, so they are two independent. I think I would leave it at the independent point right now, that there are two independent characteristics: centralized controller versus ad hoc networking. Ad hoc is more like peer-to-peer. Okay, and mesh versus non-mesh. Mesh is like Ethernet is non-mesh. Basically, you go out if you want to go out to some other place. Whereas in mesh, you can give it to some other neighbor, and the neighbor can give it to some other neighbor, and so on and so forth. And so, in that sense, it is that's what this is, mesh.
So mesh is more about the routing.
Mesh is more about the routing, yeah. All right. So there is a central coordinator called PAN coordinator. PAN is the personal area network, right? Just like the Wi-Fi access point, which allows the nodes to join the network. So if you want to join a network, you talk to the PAN coordinator, And each node has 64-bit addresses. Unlike Ethernet where you have 48-bit addresses, they have 64-bit addresses because there are many of them. Too many of them. And the coordinator assigns 16-bit solder addresses. While they want to use 64-bit, but 64-bit is just too big, so they say, okay, all right, your 64-bit is that, but we are not going to use it. We are going to give you this name. So there is a local address, which is just for the use of while communication, and that is 16-bit. The maximum frame is only 127 bytes. Where the minimum frame size on Ethernet was 64, here the maximum frame size is 127. So you see how they design a different design point. And more details later. Any question about these 5 or 6 points I told you? 15.
Frame size includes payload.
Header, everything. This is not the payload. 127 is the frame size. Okay? Payload is much smaller. Alright, so finished with the wireless. Now we come to 6th low pan. 6th low pan, the number 6 in the name indicates that it is designed for IPv6. Okay? Low stands for low power and PAN stands for personal area network. Alright, so IPv6 over low power wireless personal area network is 6th low pan. So this is actually the name of the IETF group that worked on this issue. And their job was that we have two different technologies to match. We want to carry IPv6 over 15.4. Remember, 15.4 is data link, IPv6 is network layer. So if you want to send something, you make an IPv6 packet and send it over 15.4. Now what is the problem? First problem is this thing says no more than 127 byte and this thing says no less than 1280 bytes. The minimum MTU size in IPv6 is 1280. We were talking about 64. Here it is 1280. Right? Minimum MTU size in IPv6 is 1280, whereas the maximum here is 127. And out of that 127, you could really use only 81 bytes, or maybe 81 plus 21 bytes if you wanted to be insecure. If you didn't want to be, so basically 25 bytes of header, plus this is an optional security option of 21 bytes, and then you are left with 81 bytes. So there's not much space. It's like I was going to make a cartoon, an elephant on an ant. You know, how do you send an elephant over a bunch of ants? You know, because they are so tiny things that you have to send, and the thing that you have to send is so big, right? So how do you send 1280 bytes over a media that takes only, over a data link that takes only 127 bytes, or actually 81 bytes of payload? So that is one problem. The sizes don't match. Second problem is the addresses don't match. IPv6 uses 128-bit addresses, so that is just too big. If you have to put 16-bit of source address, 16 byte of source address, 16 bytes of destination address, and so on and so forth, you know, this is wasting this payload, right? And so somehow we need to change those addresses to little quantities. Third thing is mesh routing. So now we have two layers of routing. IPv6 can do the routing, and the data link can do the routing. There is a confusion right there as to who is going to do what. Previously when we designed the layers, we designed it so that every layer had its responsibility. But now both layers are doing the same thing. Then MAC level retransmission, and then it also does retransmissions. Ethernet doesn't do retransmission, but 15.4 and most of the wireless protocols do. So here's the problem. If suppose you retransmit 15 times, what is wrong with that? By the time you are sending your fourth retransmission, TCP has already timed out and is sending a copy of the whole new packet, right? So now you have first taken big packet, divided into 15,000 pieces, and then you are retransmitting those pieces by the time a whole set of 15,000 arrives again. So this is confusing when the two layers try to do the same thing. MAC level retransmission versus end-to-end. And similar issues aside to power line and field buses. So the thing is, 6LoWPAN, even though it is designed for 15.4, actually the issues are not just local, are limited to 15.4. If you did IPv6 over power line, you will run into similar issues. Not that bad, but similar issues. Okay? So now if you understand all the issues and agree with them, then we will go to the solutions. Any questions about the issues? So first solution is to have an adaptation layer, and that does many things. First of all, if you use that layer 6LoWPAN, which is actually the name of the layer is 6LoWPAN, if you use that, and it turns out, if you go to the documents, the RFCs, they don't use the word 6 there. I mean, they just call LoWPAN. I have consistently used 6LoWPAN, but really LoWPAN is what they use. The name of the group is 6LoWPAN. But anyway, so the LoWPAN adaptation layer, what it does is that it says, okay, if you want to retransmit, please retransmit once or twice, but no more than that. Because more than that is waste of time. Upper layer will retransmit. So they allow retransmission, but only small number, like 2 or 3. Second thing they do is the headers, the extension header, they have 3 new extension headers called mesh addressing header, hop by hop broadcast, and destination processing. Now, that's another problem, is that I don't know how many of you know IPv6. How many know IPv6 extension headers? Please raise your hand. Nobody knows IPv6? Come on. They didn't teach IPv6?
Yeah, no IPv6, but don't know this extension headers.
All right. I don't know whether I want to go back again and have another one slide on IPv6. Maybe I will. But right now I don't have it. So let me just tell you, in IPv6 there were several new things. One of the new things was this 128-bit address. Second thing was that the header, instead of having one header, they said we will divide into 5-6 headers, and you don't have to have all the headers. You just choose which one you want. Right? So that way you don't have packet sizes which are big. Well, in IPv4 everything is, everybody has to have everything, right? Except for a few options. So here in IPv6 they have many headers. Some headers which are processed at every hop. Some headers which are processed only at the destination. These are all layer 3 addresses, layer 3 headers. So we call them extension headers. All right. So there is a hop by hop extension header for LoWPAN, and there is a destination address. So basically, if this header is there, this will not be seen by any router. The last router will see it. This will not be seen by any intermediate routers. The last router will see it. Hop by hop will be seen by every router. And then the message addressing header will actually change. The mess addressing header will do something which I'm going to explain in a minute. Okay. So that is 1, 2, third item is IPv6 address formation. So if everybody needs an IPv6, if you are going to talk IPv6, you need an IPv6 address. Just like if you are going to talk IPv4, you need IPv4 address and Ethernet address if you want to go on Ethernet. Remember? So your computer has a MAC address and has an IP address. Similarly, these devices have 15.4 address and they need a IPv6 address. Now, how do you get IPv6 address? You could get a DSCP and you could send a DSCP command and get an IPv6 address. But that is not how it is done in IPv6. That was the third feature in IPv6. In IPv6, they designed so that you could you can make up an address right away because there is so many addresses available, and then you can use it. So you don't need a DSCP. And so how do you do that in this case? We will talk about that. And then IPv6 and UPD compression header. So UPD, actually this is where it is mistaken, UDP. So if you have UDP on the top of IPv6, then you can save some more bytes by not transmitting some UDP port numbers. So 1, 2, 3, 4. You see, 4 modifications are done by 6 low pan. All right, so let's see.
This is a trade-off, right?
Eh?
This is a trade-off. If you use the UDP, you will also reliability. Right?
No, okay, no. You can use TCP too. No, so it's not that you cannot use TCP. But if you use UDP, they will help you reduce the size of the packet. It is not a trade-off in the sense that you don't lose anything. You don't lose anything. It just, you reduce the bytes. Okay, if you want to call it trade-off, it is a trade-off between computation and bandwidth. See here the thing. So what this 6 low pan will do is, it will do lots of computation at the beginning so that the number of bits to be sent is less. Right? It will compress the header, for example. Compression is computation, right? At the destination, it will uncompress. So you get the same information. Right? But now what you have done is you have traded off processing for networking bandwidth. You use less bandwidth but more processing. Okay? So compression basically reduces the number of bytes that will be sent. It reduces the overhead. But so basically that's what it is. Okay, all right. So one of the things you have to know is that a 6 low pan packet or frame looks like as follows. There is a frame control field, there is a sequence number, then there are addresses, security, but the most important thing to know is that there is a whole bunch of headers which are each preceded by a dispatch byte, DISPATCH, dispatch byte. So dispatch byte, that tells you what is the header about. Then there is a dispatch byte which tells you what is the header about, and so on and so forth. Alright, so we'll talk about those headers.
So
Yeah.
the headers are like the adaptation line,
The headers are
considered like the adaptation line,
other
the adaptation layer.
adaptation layer. Okay. So what happens is you get an IPv6 packet. IPv6 has its own headers and the payload. Right? This is the payload part. You take its header and compress it into like this. Okay? And now you give it to 15.4, then you chop into little pieces and give it to 15.4 after doing this. Okay, so you get the payload, you get something to be sent. You say IPv6 says I want to send this information. You first take out the header, take out the payload. Payload is you don't touch. Right? Header is what you compress. Right? So you make this big packet. Now you chop it into pieces and give it to 15.4 to send 81 bytes at a time. So this is how the 15.4 payload will look like after basically the header has been compressed. So you take the header, compress it, and you put a dispatch byte in front of it, which tells you what this header is about.
So the adaptation layer, what is its number?
What is its number? It's 2.5. So IPv6 is number 3. 15.4 is 2. Right? Okay. All right, I think I will stop right there. Maybe I could, let me see if I can finish one more slide. But basically, mesh addressing header. So one of the problems with the mesh is that you need 4 addresses. You need the original address, the destination, final destination address, and you need these intermediate addresses. When a packet is traveling from P1 to P2, it will say I am going from P1 to P2, but it is really not going from P1 to P2, it is going from O to F. Right? Actually, the same problem happens in Wi-Fi if you have multi-hop. So basically, there is a new header which is put for IPv6, in which if the dispatch byte is 10, that means it is a mesh addressing header. and that contains the addresses of the original and the final. And outside will have the address of the intermediate. Like it will say the packet is going from IPv6 address P1 to IPv6 address P2. Once it gets there, it will be assembled and they find out where it is going and put another P3 or whatever. Alright? So you need 4 addresses. The transient addresses and the final addresses. Final addresses are kept inside in this header. Okay? Now I will continue on that slide next time. By the way, those of you who want to read this up, there is only one RFC which you need to read, which is this one, 504944. It's very easy to read, very well done. Second source is this book. It's also a Safari book, and you can just read it. It's easy to read too.